that the that this ERC is going to that this ERC is going to obtain. Now, as I mentioned, technically, this is very important on line 20. This should be the only child because it's monoploid. Okay. However, if we were to entertain, because as I was going to do it anyway, but as who wants, and not just she wants, but anyone wants another example, I'll do another example. But instead of redoing everything, I'm going to use the same data so we save some time. So if you remember, there were two choices for the first letter in theory, which was the E and the K, because they both have 2 minus 2s. Now, the E wins because of the second heuristic that you go alphabetically, which is the reason why you should really only have monoploid. But if we wanted to get a close second, the Olympics, right, who's in second place, the K would be. The E was chosen already, and that's what got us this child. But imagine we chose the K. All right, so I'll put it on the same place, so that way we don't have to move the screen. So imagine the K was chosen. And let's do the algorithm again. Again, what you're going to look for is third heuristic. The more minuses, the merrier, right? And well, you can only have 2 in this case. If you have multi dimensions, you can have more, and more advanced algorithms talk about it. But the versions of it, rather, in the literature. But E and K both have 2, and no one else does. So we already chose the E because second heuristic said alphabetically E, and that's the child that became of it, and we did it already. So now we're going to do this other child, but do understand this other child can't really exist based on this heuristic. We're just doing it so that way we don't have to rewrite the data to give another example. All right, on the assumption that K is first, so the K here is chosen, and minus A minus E, so the A wins, because the A and the E are both minuses, equal footing, as it were, and therefore, alphabetically, the A is first. Okay, now we go to A, and it says minus K, but we already have the K, so it's now between the G and the I, GI minus K. And the G comes first, so we're going to choose the G. Let's write down the G. And now we go to G, and the G has A, B, C, and D, all equal level, no minuses. A has been chosen, so B is the first alphabetical letter from the G neighborhood based on the alphabetics. All right, so now we have a K, A, G, B. Okay, now we B, and now we have minus H. The minus wins because minus is, again, more minuses the merrier, third heuristic. So the H is the next letter, not the G and J, although alphabetically first, they aren't minuses. Now the B minus B would win, but it's already been chosen, so the I comes first. So I is now the chosen neighbor of H. Okay, I has been chosen. A has been chosen. F has not been chosen. So F is now the neighbor of I. Okay, we go to F. J has not been chosen. J is wins because of the minus. So J is the neighbor of F. A has been chosen. F is minus, but F has been chosen on the neighbor of J. Right? If you look at the second child here, the J has been chosen. So B and I, here's the case, another case. Oh, this is good. This is good. The B and the I. So look at J. F would win, but minus F, but F already appears. So now B and I is left of the neighbors of J, but both those appear. Now we're stuck. So who do you start with? So again, Wikipedia would say randomly choose from the availables, whereas our version second heuristic is the alphabetic wins. So who is the first letter that wins? So this is the detail here, you have to say. It really should be, it's the first alphabetics, but don't remember, don't forget, the second heuristic doesn't operate independent of the third heuristic. So it's the who do we choose? We choose the alphabetics amongst the available data values who have the same number of minuses. So imagine there was no minus for the C. Right, C has not yet been chosen. Imagine it says D minus E, G. Imagine the E did not have a minus, and instead the neighborhood of C was D, E, G, whatever. That would not be chosen because the D does have a minus. So it's not that the second heuristic kicks in without the third. All three operate at the same time. So the alphabetics win, but the more minuses, the better. In fact, based on this, I think I should write this first, because I think it'll be less confusing. How do I write this first? Oh, I have an idea. It's going to be better. Because we just mentioned the minus in the first heuristic. And now we're saying the more minuses, the better. But let's say there's a tie, so the tie would go. Then only afterwards the alphabetics. Okay, I think that'll be much more clear. Anyway, the C wins because it is the first alphabetics, and it's also equal number of minuses. Oh, no. Sorry, the E wins. The E was not yet chosen. I forgot. I forget when the second child. Well, again, that child can't exist according to these two heuristics. But anyway, E has 2 minuses, so the E is the most minuses, and no one compares. The K has already been chosen. E would be next. Interesting. The E is next. Huh. Interesting. The E is next. Wow. Okay. Now the E has a C and a K, so the C would be chosen next because it's C and K. K has already been chosen, so then it'd be C. Let's see. There was a comment. Hold on. Why did we go with C? Why didn't we go with C? Yeah. Waleed asked, why didn't we? Yeah, correct. Good question. All right, so let's repeat that. The reason is, look at the way I wrote. You see, the heuristics don't operate independently. They all operate in unison. So it's not just the first alphabet letter wins. It's also more minuses wins. Now E has the most minuses. D and C and D have only 1 minus. But E was available at that point. When we were up to J, E was available. And E has 2 minuses. Okay? So therefore, the E would win because the second heuristic kicks in, more minuses, and there's no parallel. Well, K has 2 minuses. K has already been chosen. It's the first letter in this child. That's why we chose E over C and D. C and D are earlier been chosen, but they only have 1 minus. E was not yet chosen at the point of J, but has 2 minuses. And the second heuristic kicks in. All right, Waleed, does that answer your question? Okay. Here. At this point, on the left, when you're up to J, okay, even without left, okay. At the point that we've now done J, who is available? The C, the D, the E, and the M, right? Please confirm, Waleed. At the point that we just did the J, the C, the D, the E, and the M is available. Is that true? Okay. So now you catch it. Good. The C, the D, and the M only have 1 minus. So although, according to heuristic 3, the C would have been chosen, the E actually is chosen because you also need heuristic 2. And heuristic 2 says the more minuses, the better. And E does not have a tie because K has already been chosen. So the E is chosen. Okay, Waleed? Is that more clear? Yeah, good. Excellent. Okay, good. Yeah, pleasure. Very good. Good question. All right, so after the J, we've decided to take the E, which is 2 minuses, the K, C and K. C is then chosen because that has a minus and it's also first, but also K has already been chosen. All right, so C now goes next. So let's choose the C. The E would have been the minus. The neighborhood of C is the minus, but it's already been chosen. And the D has not yet been chosen, so the D is the tie. Right, so that's, again, the heuristic. Oh, here it is. Waleed, it's very interesting. Here's the same issue at a microcosm level. C has a D, a minus, E, and a G. So the minus E would have won over the D. Why does the minus E win over the D, even though there's a tie and D now should have been chosen first because D is before E? The answer is because it has more minuses. Now, it turns out that we don't use it because it's already been chosen. But otherwise, the minus E would have won over the D. Anyway, same idea. All right, so now we choose the D, and now the minus is at the M, and we've never done that an M. So now it's an M here. And now we choose, oh, then we're done. There's nothing else left. Okay, so these are the two children. Again, I'm going to put this in parentheses, as it were, because officially this child cannot exist. But pedagogically, I gave it an example instead of ahead and rewriting and randomly choosing another set of parents. Okay, so Shu, did that help you as well? Hopefully you caught it now. Okay, good. All right, so that's the respectful crossover. Yippee. Yeah, thank you. Okay, now, so again, admittedly in the literature, even as I said, Wikipedia even just already doesn't use the third heuristic. Wikipedia only uses the second heuristic, and then randomly chooses amongst the available choices. Wikipedia, but we don't. This is the original paper, the way we did it. All right, now so that's it. And then again, the fancier, neighbors, and multi-dimensional graph structures, blah blah blah, and not blah blah blah. But we don't have time to do it, and it's very advanced stuff. So if you want, you can read many research papers on this. All right, so that is the ERC example. Okay, good. Let me label it such; it'll be easier to find. And now let's talk about respectful mutations. Unfortunately, respectful mutations are much easier, much more simple to understand, for pretty much the same reason that we've said up till now, which is that you don't really want mutation to do too much. You want it to give it a little bit of a kick, so that way you get innovation, as it's sometimes called, variety, right? You want innovation and variety in the genetic material. Right, you want what's called innovation. That's sometimes what it's called, or variety in the genetic material. But you don't want to change too much. That's never been good in the genetic material, but not too rapidly. As I said, as much as the case you made it counterintuitive or not, random algorithms just don't do well. Not in these complex problems. Typically not. All right, so let's go through what's called the respectful, respectful mutations. All right, so, okay, fine. All right, so the first one is, the first one is very trivial. All right, we need an example. All right, let's pick some data here. I'm going to use pretty much the same data all the time. All right, and so not that. Let's take a simpler version. All right, so imagine this is our individual. 1, 2, 4, 5, 6, 7, 3, 8. So that's the permutation of the numbers 1 through 9. Okay. All right. And that's our individual or chromosome that we have. Now we want to do mutation. All right, so let's imagine that we did a 1 point, as it were, 1 point mutation. But you randomly choose a point for a mutation. All right, and let's imagine, okay. So let's see here. Somebody randomly pick a point. Which number should, okay, it'll be a little confusing. Let me say it differently. Randomly pick one of those numbers that we're going to mutate. Somebody? Which number should we mutate? Just randomly pick 6. Okay, now someone else tell me what we should mutate 6 into. Someone else pick a different number. 6 goes to 8. Follow us, let's say. Beautiful. 6 goes to 8. Okay, now watch. So, actually, for editing purposes, let me put this separate. It'll look a little easier to read. Good. All right, so, yeah, actually, let's expand that. All right, now, so we mutated what we do. So mutation step 1. Well, it's part of the process, but then we have okay, so we said, okay, the 6, Austin says, and Vala says it goes into an 8. All right, so the 6 became an 8, which now we have a commission-omission problem, right? Commission that there are now of 2 8s. And omission in that we don't have a omission of the 6. All right, so how do we... What's going on here? 1 second. of the 6. Good. Now, so how do we resolve it? Resolved. So this is going to be the true mutation. By simply changing the, notice the other 8, change it to a 6. Ta-da! Right? Let me order this. Let me organize this so it's all lined up a little bit better. I'm trying to make it lined up so it's a little easier to see. No, that's not good. One more. Yeah. All right, that's good. That's good. And now let's move this over, which means you have to move these guys over. Okay, one more, and I think we're okay. Yeah, that's beautiful. Okay. All right, so let's move this over. So that's what happens, right? So the 1.8 became a 6. So what do? Well, where the commission 8 is, the original 8, you now make a 6 because that's the only one available. So that's the trivial 1-point mutation. Very straightforward. So we'll call that. I don't know. Actually, it's so. I hate to say it's so trivial. I don't even know in the literature if they actually do this. I may have created this myself, but this is sort of a pretty easy 1-point mutation. However, it is a valid method, so we're going to do it. So that is 1-point mutation, and it's respectful. All right, any question of what we will call 1-point mutation? You know what I'll do? Let me put this in red, so that way it's easier to realize what's going on. There's the commission, and now we resolved it. Good. All right, number 2. Okay, so number 2 is called a insertion mutation. Right, insertion mutation. And in this case of insertion, I'm sorry. I could do insertion mutation. Let me do inversion. It's a little easier. Let's do inversion first, and then we'll do insertion. Because this insertion and displacement, which is similar. Let's do inversion. It'll be a little easier. All right, so here's our individual, and now we have a range, meaning we want to mutate so it's a 2-point mutation. 2-point in the sense of the 2-point crossover. We're going to mutate a range, a region. All right, so let's imagine 4, 5, 6, and 7 is going to be the region that you're going to mutate. All right, so inversion is to invert, is like reverse. So the mutation will be as follows. Actually, you know what? I don't think we need so many spaces. All right, so now how do we do that? We're going to do as follows: 7, 6, 5, 4. We invert the numbers. So we take the 4, 5, 6, 7 from left to right. We invert it. So now they're from right to left, as it were. So it's 7, 6, 5, 4. Very straightforward. Again, all of these are going to be very, very easy. I just wanted the comments on the same columns. All right, any question on inversion mutation? It's pretty straightforward, I think. All right, so insertion mutation. Insertion mutation is a 1-point way of dealing with 1-point mutation. So let's take the same individual, original individual. There's the data here. All right, let me get out. Let's take away these brackets. It's not a region, it's only 1 point. All right, give me 1 second. Give me 1 second. Yeah, okay, good. All right, so somebody randomly pick a point, one of the numbers. Let's go, instead of the position, it's confusing. Somebody randomly pick one of the values. Okay, Andrew picks a 1. So we're gonna put it somewhere. Tell me, someone else tell me, after which number, I'm sorry, in line 60 we always put the omission at last position. No, it turns out that way. Look at line 5, it turns out that way. The 8 in the brackets is the same number as the last one. It just turned out that way. Okay, Shugwa? Okay, very good. All right, now, so Andrew said we're going to mutate the 1. The way insertion works, tell me where to put it. After which number? So after 7 vola sets. Excellent. All right. Andrew chose the 1. So we're going to quote unquote mutate. So the mutation is going to be, and Volha says, let me see what number he or she chose, 7. Okay, so it's going to go after the 7, and let's copy this over and change it. So then the 1 is going to, over in the second one, yeah. So the 1 is going to go after the 7. All right, and you could drop the brackets, but I'm doing that for emphasis. All right, so the 1 was chosen, the data value 1 was chosen for mutation, and the insertion point was randomly chosen to be after the 7, after the data value 7. Okay, so that's insertion mutation, and that's a 1-point mutation. Now, you could also say, what about a 2-point? What about a regional? So that's called displacement. Okay, so, well, I'm going to change the values in a second. Let me just write these numbers for displacement. Okay, so we have a regional. So let's take the 4, 5, 6, and 7 again, only because that's the example we used above. Not that it had to be that way, but let's just imagine. So imagine the region for displacement is 4, 5, 6, and 7. And now somebody randomly choose a insertion point, which is called the displacement point. That's the way they call it for this region of 4, 5, 6, and 7. Somebody randomly pick a point. Okay, 1. Very good. All right, you want 1? Very good. So let's do that. I have to change the comments in a second. So the 4, 5, 6, and 7 will now go after the 1. Okay, so the region 4, 5, 6, 7 was chosen for mutation. And the displacement point was randomly chosen to be after the data value 1. Good. Any questions on that? Beautiful. Very, very good. All right, last one. The last one takes a little bit of thought, not terrible thought, a little bit of thought. And that last one, it's a little bit of busy work, as you'll see. It's called a heuristic mutation. All right, that's its name. Now, the heuristic mutation is a class of mutations in that you make up the heuristic, as you'll see. But anyway, that's a fact. And let me give you an example of it, and then you'll see where you're allowed to insert your own, input your own heuristic. All right, I see your question. Okay, Waleed asked the following. So essentially, insertion and displacement are the same exact displacement, except, yes, that's correct. That's right, Waleed, exactly the case. Yep, good. Good way of summarizing. Okay, heuristic. So let's take heuristic. Yeah, we can take ours. All right, you know what? Let's take ours. Okay, now I have to do a little bit more work in order to make this look nicer, or well, not just nicer, but that we understand what's going on. 9, 1, 2, 4, 5, 6, 7, 3, 8. Okay, so that was our original. That's our original seed. Chromosome, individual. All right, and just to prove that, let's do a text join. Oops. So you see the entire thing together. Text join, no delimiter, skip spaces, and then let's put this all together. All right. All right, so that's our individual. All right, now, all right. Somebody randomly pick 3 numbers. Okay, spread them around. You don't have to, but let's say don't choose them all next to each other. Somebody randomly pick 3 numbers. Anybody? Okay, 6, 1, and 4. Excellent. Thank you. Perfect. No, 6, 1, and 4 has already been chosen. 6, 1, and 4. All right, so these are the points. So in this case, you could think of it as a uniform. It starts out to be a uniform. It's akin to a uniform crossover. Uniform mutation, okay. Well, crossover, but the point is it's bit by bit. All right, so that's how you start. Okay, this is only how you start. Now, from a notion of permutation, if you have 1, 4, and 6, there are okay, you chose 3 places, right? You chose a 1, a 4, and a 6. So there are 3 x's, right? Move that over. So there are 3 x's. And there are 3 factorial ways of keeping those x's in their relative places, but mutating them. So, example, okay, let's, okay, let me just keep this like this, so you can concentrate. Everything else is the same, right? Everything else stays the same. I think, well, okay, fine. Let's leave the rest as is. Now, so what happens? 1, 4, 6, 1, 6, 4, 4, 1, 6, 4, 6, 1, and then 6, 1, 4, and 6, 4, 1. All right, let me just center that so it looks a little nicer, and let's copy them over. So these are all going to be yellow, yellow, and yellow, again, to emphasize that this is the column we want. Okay, now let's copy this down. Oops. That's interesting. Okay, good. And let's copy these now. All right, so now let's do text join. So these are, it looks very similar, but if you look carefully, these are the 6 possible ways of permuting the points that are to be mutated. Now, we're going to apply heuristic and choose one of these. I should mention, though, it's up to you whether you want 5 or 6. What I mean is that this was the original. Right, this right here, 1 second, let me underline it so you can see it clearly. Right, this one here was the original. Do you want to include the original as the possibility? The problem is that the heuristic may actually say that the original is better than the others. So it's up to you. We'll put that as a note. Okay, now, so let's summarize. To summarize up to this point, there's still one more step, which is the heuristic. We didn't do the heuristic yet. To summarize up to this point, 3 points were randomly chosen for mutation. Shuffling, well, that's true. Shuffling these around in place. Shuffling these values, data values, around in place yields 3 factorial or 6 possibilities. Note, I'll put it here already. Note, as to whether the original data, the original chromosome individual should be considered now is up to you. All right, for the purpose of exams, I will include it. For purposes of exams, I will include it. So you should know I am including it. All right, so now we want a heuristic. Now, we want a heuristic that, okay, the very important point. Please note, I did this only so I don't want to confuse you with everything. Note, we want to note, a very important note, the heuristic was given before we got to the data. The heuristic has to be given before the GA starts. Okay. So we're only going to create a heuristic right now together, but understand you're not allowed to do that. In heuristic mutation, the mutation operator exists before you get started. I'm doing this pedagogically because I want to confuse you. I want you to see the steps clearly. So I'm putting the heuristic operator, the heuristic aspect now. But understand, this should have been discussed before we got started. Okay, now we want a heuristic to evaluate each of the possible chromosomes